Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to continue our discussion talking about GPS error by talking about something that is sort of more fundamental than the sources of error that we talked about previously. Right? Previously, we talked about the errors that occur when the satellite is communicating with the receiver, but there's actually something more structural at play that sort of transcends all those other errors. And that is something called viewing geometry. Right? Viewing geometry. And basically, viewing geometry is the relationship between the satellites and each other, and the satellites and the receiver. So, for example, if we were to sketch out sort of the examples that we've had before, right? We have the Earth here. On the Earth, we have our little person, right? This is you, right, with your little receiver here. Right, and you're collecting information from the satellites that are on the horizon. Well, viewing geometry would be the relationship between the satellites and the receiver, right? In this case, right, all three of the satellites are kind of directly overhead. Right, we could draw another example of viewing geometry over here, right, where the satellites are more, let's not have him be green, let's have him be white. Okay, you have another example over here, right, where the person has his little receiver, but the satellites, instead of being all completely overhead of the horizon relative to the person, right, maybe you have one over here, you have one sort of overhead like before, and then you have one sort of on the other side of the horizon, right? These are two different viewing geometries, right, because the satellites are in different places relative to the receiver, right? In this case, they're sort of clustered up, and in this case, they're sort of more spread out. Right, so viewing geometry, to sort of put it simply, is the geometric relationship between the satellites and the receiver. Right, in this case, right, this is kind of a bad geometry. Right, and it's a bad geometry because the satellites are too clustered. Right, in this case, right, this is a good geometry, or a better, I should say, maybe it's a better geometry. Because the satellites in this case are more spread out, are more spaced out, right? More spaced out, right? So again, in both cases, right, the viewing geometry is this relationship between the receiver and the satellites. In this case, right, they're all sort of at a very narrow angle. Right here, you have a couple that are at a more shallow angle and a couple that are more steep angle relative to the receiver, right? So viewing geometry is just this relationship geometrically between the receiver and the satellites. And as a general rule, and I'm going to write this in green, I'm going to star it here, right? General rule, right? More spaced out is better. Right, you want to have your satellites with more sort of different angles relative to the receiver to be able to give you a better viewing geometry to give you more accurate results. Right? That's why I said this was better, right? Because they're more spaced out. This was worse because they're more clustered, right? And so you might be asking yourself, okay, well, why does this matter? Why do we care about this viewing geometry? And why do I say that it's better to have them more spaced out? Well, let's go ahead and look at two diagrams that I think will explain this much more clearly than I have here. So let's go ahead and scroll down a little bit. Okay, so this is an example of good viewing geometry, relatively speaking, right? Because the satellites are kind of a little more spaced out, right? Versus if we slide over to the left here and we compare it to here, right, you can see that they're kind of all on top of each other here. I'm going to zoom out just a little bit so we can have them both on the screen at once, maybe a little bit more. Okay, so of the two, I'm making the claim that this is a better viewing geometry than this. And the reason I say that is the positions of the satellites are more spaced out relative to this, right? The sizes of the circles, which represent the signal distance, are the same, right? Nothing has changed. The only difference between these two things is the positions of the satellites. So in this case, they're more clustered, and in this case, they're more spread out. And what I want you to focus on here is two things. First off is the bands, right? So I've taken our trilateration example from a couple of videos ago. I've painstakingly replicated it with perfect circles, and I've expanded it to include that idea of error that we talked about in the previous video. So basically what I've done is your red satellite, given the errors that we've talked about, is confident that you're somewhere between this dashed line and that dashed line, right? Now we have this sort of zone, if you will, for the red satellite, that when you receive the signal, you're confident that you're somewhere in this zone rather than on a specific line. Same thing with the blue and the same thing with the yellow. So if we take our trilateration example, where we were saying, okay, well, we have these three satellites and we know where we are because we find the place where those three lines intersect, we can do the same thing here with this, extending it out into this idea of error by looking at the area, right, where the sort of zones intersect. So if we zoom in just really quickly here, kind of center it just a little bit, right, you can see here that the yellow band, the blue band, and the red band, right, this green area here, right, this is where all three of those bands overlap. So if you were getting information from these three satellites, just like we did with the regular trilateration, right, you would be confident that you were somewhere in this green little, almost looks like a squashed diamond here. Okay. Now the reason I say this is a better viewing geometry is if we were to zoom back out a little bit, scroll back over, right, visually we can see, again, nothing has changed on the right-hand side here except for the fact that I've moved the satellites closer together, right? I've made that viewing geometry, as I stated before, generally speaking, less well. Like, this is a poorer geometry because the satellites are more sort of clustered together. And you can see that that translates directly into the area, right? Over here where we had a little bit more space, right? The little squished polygon here was much smaller. Over here, as the satellites begin to move closer and closer and closer together, right, we start to see that the area where we are confident begins to get larger and larger and larger and larger. Now, this would, to take this to the extreme, right? I didn't diagram this, but take this to the extreme, where you had three satellites that had the same sort of error characteristics on top of each other, right? At that point, they would be the entire zone, right? That's if you took it to the extreme example where they're on top of each other. But you can see here that the farther apart the satellites are relative to the receiver, right, the more confident we can become, even if we have error. Right, the more confident we can become in our answer here. And so this is irrespective of the errors we talked about before. This is just based on the geometry of the satellites. Right, that the farther apart, like the more spread out they are in their constellation, the overall better we're going to be in terms of getting an accurate measurement. The closer they are together, right, the more their bands overlap, the less accurate we can or confident we can feel, right? Because this area is much larger than this area. So I know this is a little bit complicated. I encourage you to rewatch this part a couple times until you really feel comfortable with this transition from the basic circular trilateration that we talked about to this zone we created by including error, and the way that the shape of that overlap changes as we move the satellites closer together, right? As we create a poorer viewing geometry. right? This is a better viewing geometry. I'm not saying it's perfect. This is a better viewing geometry than this because the satellites are more spaced out relative to here where they're kind of clustered together. And you can again see that by comparing the area of the overlapped regions. And you can see in this case versus this is a much larger area than that. So hopefully this all makes sense. And as always, if you have any questions, please reach out. Thank you.